everybody. Thank you very much for attending to this meeting. It's always a pleasure. And so we are lucky today because so you know that we had a big event for the astronomy community, which is this NOVA RS Ophuchi. And we are very happy that we can have this presentation by François Teyssier and Steve Shaw about these observations. And I want to thank you very, very much to both of you. And thank you for your time. Thank you for your effort. And now I'll let Olivier do the presentation for the practical things. Thank you.
Okay, thank you, François. This meeting is we have a free party in this meeting. First, we have a presentation about 30 minutes with François Teyssier. Then Professor Steve Shaw gave a presentation about also 30 minutes. And then we have a question and answer with all attendees. So now, François, you have the microphone and you can...
Okay. Take it. Is it correct?
Yes.
Yes, you hear me? Okay.
Yes. Go for it.
Okay, good. So, come back to this fantastic event in RS Ophuchi. This is a NOVA first, which means an explosive event, thermonuclear novae, in the degenerated envelope of in the envelope accreted from a main second star or white giant at the surface of a white dwarf. Generally speaking, the recurrence of novae events is hundreds or thousand years for the so-called classical novae, which has been observed only one time. But for novae, which have been observed several times in the modern times, say since 100 years, we call them recurrent novae. Recurrent novae are very few as number. About 10 in the Milky Way have been observed. And 5 of them are, in fact, symbiotic novae. The difference between a classical nova and a symbiotic nova is the size of the donor star. In novae, classical, very classical, the donor star is a main sequence star. In a symbiotic nova, the donor star is a white giant. And in symbiotic TCRB type recurrent novae, such as TCRB, RS Ophuchi, and so on, 5 known at the date, the donor star is a white giant. Here is the previous nova events in RS Ophuchi with a very short recurrence time scale of about 20 years. The last outburst has been observed in 26. This is from AVSO data, the blue points. And we have the current outburst in 2021 in red, with a maximum which appeared at about 9th of August. The rise has been very quick, about 1 day, a little bit more than 1 day, by 6 magnitudes in V band, and the decline is for nova fast, with decreasing magnitude of 2 magnitudes in about 5 days. Here is, as a tribute, a spectrum obtained by Christian Buil in on 26, which has been used for publication by Augustine Skopal. Here is the first spectrum of the event in the database, which has been obtained by Jean-Bruno Desrosiers in Canada with an ALPI at low resolution, and showing the classical spectrum of nova near the maximum luminosity, with essentially an absorption spectrum and faint, relatively faint emissions of Balmer lines. Before the nova event, I want to keep back to RS Ophuchi in questions with this simplified model of this special symbiotic star. A red giant which has a low mass, and early M giant spectrum, which probably fields or near fields is its lobe roche. The accreting star, a white dwarf, develops an envelope with the material sent by the donor star at a very high accretion rate. The second very important point to understand the recurrent nova in symbiotic stars is to consider that the white dwarf is very massive. The typical mass of a white dwarf is 0.6 solar mass. Here we are in the case where the white dwarf is near the Chandrasekhar limit. There is probably an accretion disk, and the accretion comes probably either from the material of the red giant itself, or the very massive weight wind from the red giant through the Lagrangian point 1. We have an accreting envelope which is degenerated. It is that it doesn't react as a perfect gas. In bold, the main difference according to a typical symbiotic star. Here is from our monitoring, and the last spectrum we have got in quiescence by Pavel Dubovsky at a resolution of 1000, with, in fact, for a symbiotic star, a low level of ionization, with, of course, Balmer lines, helium lines, and essentially ion 2 lines. But one can see that, for instance, helium 2 is missing. It is that the ionization temperature is somewhat low for a symbiotic star. And note that we have no trace of the forbidden lines N2 or O3. This is important for the development of the nova event. Here is from a shell spectrum obtained by Tim Lester, the typical profiles of RS Oph in quiescent state with H alpha line, for instance, very broad component, about 2,000 kilometers per second. And this very broad component, a typical narrow line of about 150 kilometers per second, and a deep absorption near the systemic velocity. Here is a crop of H alpha line showing the very broad emission at the pedestal of the line. Here is some lines, H beta, with a very deep central absorption under the level of the continuum. And I give some examples of the FWHM of a few lines at somewhat more than 100 kilometers per second, with a double-peaked I1-2 line, perhaps from form in the disk, perhaps. And sorry, here, oxygen 1 forbidden line, which is very narrow, about 40 kilometers per second, and thus probably form, in fact, in the symbiotic nebula. Yeah? Because this is approximately the speed of the ejecta from the red giant. So the outburst, not in detail, of course, from the accretion of hydrogen and helium at the surface of the white dwarf, the mass of the envelope has increased, the pressure has increased until it weighs the critical pressure for which the thermonuclear runaway develops. Following this thermonuclear runaway, at a time scale of a few minutes, the temperature rises very quickly and reaches the so-called temperature of Fermi. At that temperature, the degeneracy of the envelope is removed. Thus, all the material, helium and hydrogen in the envelope reacts as a perfect gas. It provokes the expanding of the envelope, and at a certain moment, an ejecta, which can be bipolar, and also eventually a fast wind. The velocity of the ejecta is very high for nova, about 3,000 kilometers per second. The main difference, according to a classical nova, is that the ejecta and eventually the wind will collide with the wind of the red giant, which is a source of very high energy. Here is a spectrum secured by Pavel Dubovsky, just 0.5 days day after the maximum luminosity, showing very quickly the development of the spectrum with helium lines, there and there, and also development of Balmer lines. And even at that resolution, we see that the profile of essentially Balmer lines is a composite profile with a broad component and a very narrow component. It will be easier on this spectrum obtained with an Echelle spectrograph at the same date with helium there, and the Balmer lines here, H alpha, H beta, with the broad component with a narrow emission, and also, we'll see that in detail, narrow absorption. We have about the same, again, for helium and ion 2 lines. Here is the development of the spectrum from LISA spectra with here the light curve obtained by EVSO V-band data, and the development of the spectrum with the first spectrum obtained by Jean Bruno Desrosiers, very flat, essentially absorption, and the development very quickly of helium lines, but also now nitrogen forbidden lines, C3, and after we have the development of helium 2 or oxygen 3 forbidden lines, which means that there is an hardening of the ionization source. Here is at resolution of Echelle, say resolution 10,000, the profile of H alpha line with their quark to the central region between with a range of 800 kilometers per second, and we see clearly the broad component about triangular at 3,000 kilometers per second, and the narrow component which has velocity of about 50 kilometers per second, and a narrow emission which is displaced about for the minimum of the absorption to about 70 kilometers per second. The same, so we again with HA1 line, with of course the sodium absorption, yeah, but we have no trace of emission of sodium. Here we can see how the spectrum is complex due to the very high speed of the ejector, with the line of helium 1 and ion 2 at 4,922-24, with here the blend of the broad emission, and there the two emissions from this one ion 2, this one from helium 1, and their respective absorptions. It can be compared to the almost pure line of the same, sorry, here with 42, of the same multiplet line at 5167 with only one emission and one absorption. In fact, what happens is that at the state, we have, of course, the envelope which has increased at a very large radius, about giant dimension, in fact, the ejector, and very sorry, and we have strong UV photoionization of the nebula. The spectrum, the profile of the line, can be understood for the broad component as produced by the very fast ejecta with radial velocities of about 3,000 kilometers per second. The ionization of the nebula, the dense symbiotic nebula, will produce a narrow emission line because the velocity of the red giant ring is about 20 or 30 kilometers per second. But we have also part of the nebula which remained under the ionization front, which can produce absorption. 3. At the time, we have gathered almost 2,000 spectra of the event in the database, and we have, this is very special, daily monitoring with HL spectra, with a very, which allows a very fine timing at minus plus 0.d of the major events, and notably the rise of ionized lines. This daily monitoring allowed us, for the first time, I think, to detect fluctuations which were unknown despite the modern observations of several events in RS Ophuchi. This presentation, I use essentially HL spectra secured by the team. Here, I will go very fast because this is just line identification, but it will be in the PowerPoint. Development of H alpha line, according in 3D graphic, with there the first spectrum showing the triangular broad component and the narrow emission. The same in contour plot, with always the narrow component. Helium 1, Fe2 line, and thus there now more conventional treatment with the profiles that we obtain daily from HL spectra, with the flux in log scale. For now, it is only relative flux. We shall have to use AVSO data in order to calibrate in flux the spectra. And thus the very preliminary results essentially to show, of course, the development of the intensity of the line according to the continuum, but also to show the consistency of our data. Here is from an automated tool with Python, the equivalent weights of H alpha. The same for helium-1. I think this is really very robust results. Now, we have had detection of narrow lines also with only a narrow component. Here is, for instance, nitrogen 2. There's a little problem with the automated correction of heliocentric radial velocity in my Python tool. So I will have to correct those spectra. But in fact, the radial velocity remains the same. But you can see that this is only a narrow line with FWHM of about 46 kilometers per second. And with the same very nice evolution of the equivalent width of the line, which of course will be translated in absolute flux with AVSO data. Thanks to the very large range of Newt spectroscope built by Juan Guaro and his two observatories in the north of Spain, we have a very nice monitoring of oxygen 1 lines in the near IR range. Very interesting because the profiles of the lines are very, very different. They are produced by different physical interactions between light and material. The same for O3. O3 forbidden lines, which increases in the blue part of the blend formed by helium and iron 2, and there the development of oxygen 3, and the second line of oxygen 3 in this one. This is also now line formed in the symbiotic nebula and not in the ejecta. Now we are at the state where the thermonuclear runaway is ending, and the envelope will begin to retract, and it is still a perfect gas, and so the temperature will increase with the retractation. What I don't know in English. The envelope collides, in fact. And we shall have, as the temperature increases, development of far UV, soft X-rays, and thus an increase of the ionization states of the different atoms. Here is, for instance, the development of helium-2 which has a ionization energy of 55 electron volts. This is a recombination line. And we can deduce from our very precise monitoring the appearance of the line at day 16 after maximum luminosity. And thanks to our excellent monitoring, we can detect, I think this is the first time, that this line has faded in the time scale of about 1 day. This is, from my knowledge, the first detection of a rapid variation during an outburst of RS Ophuchi, and a very important, which will be difficult to explain, of course. The result was so unexpected that we used for the elaboration of the astronomer's telegram low resolution spectra for confirmation. Here the development of the equivalent weights. I think that this is subject to debates. I think that we have detected Raman O6 band, which is in fact the Raman scattering of O6 in the far UV. I think we have detected them on day 19, and the same as helium-2, we have variations, sorry again, of this line. Here, it has faded. We are in now increasing temperature of the ionizing source, and we can detect higher ionized species, such as iron 7, with a nice curve of growth. Well, here is where we are, sorry. It's just 1 day candency monitoring with HL spectra. We have produced very good monitoring, but thanks to David Boyle, I see that professionals become not so bad. With Ulysse Munawi and his colleague has produced something which is very good for professions. We undergo the monitoring at the same cadency as far as possible. And now we have a colleague in Australia, Colin Edwidge, with an HL Sheliak spectrograph, who will help to have the monitoring the long as possible, as the RS Ophuchi will go to conjunctions, sorry, with the sun. Before leaving you, I want to insist on the fact that another recurrent nova, T Corona Borealis, could explode as a nova for the first time since 1945. Here is the comparison of the light curves with diamonds in 1945 event, and the current light curve in B-band obtained by AVSO observers. And it is very probable that the next nova outburst of TCRB will happen in 1 or 2 years. So we have to monitor TCRB not only during the nova event, but also before the nova event, in order to gather scientific data of the pre-outburst phase of TCRB. The last Echelle spectrum obtained by Juan Guaro. Yes, I finished now. Thank you very much for all the observators who are contributing to the monitoring. In only 20 minutes, I have not developed important result obtained by Christian Guil and Pierre Dubreuil in the near UV range with UVX and SOLEX. And I want to renew my very deep gratitude to Steve for his tireless support. For the astronomers telegram, we should add their Juan Guaro and their Stéphane Charbonnel. Some lecture, a text produced by Steve, another one by Augustine Skopal and Natalia Shgatova, and the very comprehensive thesis of Alessandra Azzolini about the explosive outbursts in symbiotic like recurrent nova. Thank you very much, and now I lay the place to my mentor, Steve.
So, should people just take a breather here? They might have to go to the bathroom, or should we just keep going?
Keep going.
Oh. Okay. Francois, that was beautiful. I'll get to a couple of points first. Something about sort of the basic physics producing what we're seeing and why it matters. And then kind of try to put this in context. The thing to keep in mind always is that novae are comparatively simple things. You can think of it this way. You have a pile of compost that you've been accumulating in the garden for 10 or 20 or 50 years, or 10,000 years, depending on how you put the material in. And gradually this compacts. Now, if you do this on a normal star, because it's an ordinary gas, it's going to heat up. And if you accrete material, it means you're releasing energy, which is incorporated into a restructuring of the envelope. So as you're accreting, the object is going to become more massive, and its increased gravitational field is going to produce a reaction in the gas, which is going to expand it. Okay, so this is basically the process of building a star. In star formation, what you're doing is taking a regular gas and putting it onto something that's a self-gravitating regular gas. Now, the thing that gets you into this later state that some systems are called just cataclysmics, others are specialized and called symbiotics, is that in the course of evolution, in the binary system, one of the stars has succeeded in stripping. Now, this is an important point because it's the difference between the initial state of a system like RS Oph and the initial state of the novae that many of you are used to, those that we usually call classical novae. The main thing is that if you have, well, we'll just take a symbiotic star. You have a giant, a white dwarf, and the white dwarf is sometimes the more massive star in the system. Now, you all know that in the course of stellar evolution, the nuclear processes in the core are going to alter the composition. And if the outer layers of the star can be stripped off, once the system is not sufficiently massive or has succeeded in burning its nuclear fuel to the point where it can't process anymore, it has no choice. It cools. It's the same thing as taking a person in the middle of the winter in Antarctica and throwing them out into the cold and then stripping off their clothes. You know, they're going to die. Now, they may not contract very much, but that has to do with the structure of the human body. On the other hand, they are going to cool. Okay? Now, if you've got something that's about a solar mass, it takes a while for that object to cool to zero, but effectively, as it's cooling, it's going to have to restructure itself, so it's going to contract. And if the star is sufficiently massive, but not too massive, it can find a new equilibrium, and that's called a white dwarf. So it's an object about the size of the Earth, of order a solar mass, and because it's sufficiently compact, has a density about 10 to the 4 times that of diamond. What you've got is a structure that can be heated, but isn't going to physically expand because of that. Now, you're used to things like this, the difference between heating a balloon filled with air and a balloon filled with water. Okay? The water is going to expand, but it's going to expand very little. This is essentially a degenerate configuration. But if you put this in an ideal gas, it's going to expand very rapidly. Okay? I hope this point is clear. Now, the key difference is that if you pile enough material onto it, however that matter gets there, if the white dwarf isn't in isolation and can accumulate mass, eventually you could build up a layer in which the pressures are sufficiently high that you trigger a nuclear reaction. This happens in an environment that, because it's heating and because, and this is important, the electrons are degenerate, but the protons and ions are not. And so the heat gets dumped into the motion of the other material, that is, of the nuclei. And obviously there's a difference because it's being heated here and up here it's not. This starts a convection, okay? And that goes to turbulence, and that mixes material from the interior out into the envelope. Now, let me just do some cartoons here, so it may make life easier. And if anybody wants, please, to interrupt, I would greatly appreciate that. Okay, so I hope you can see my whiteboard.
Yes.
Okay, so the idea is you have here material that will say here is the white dwarf, and this is the stuff you've been composting over all these years in a layer above it. Now, this is part of the problem that's directly related to the occurrence of the nova explosion, but also specific to recurrence. François mentioned that in the galaxy, there are only a few known recurrent novae. And this is in part because we've got this problem, and the galaxy is full of crap called the interstellar medium. And most of the stars that are going to be the most active are where most of the stars are, and most of the young stars, which means toward the center of the galaxy and seen through a lot of dust. So there's a real problem with discovering these. And to say that something is a recurrent also means, again, as François had mentioned, that it has to have recurred sometime in the historic past. That's a difficulty because novae just ain't that bright. These aren't supernovae or hypernovae. They're just ordinary novae. And so they might be noticed or they might not. Ophiuchus happens to be not the best placed object in a constellation in the sky for the northern hemisphere. And in the southern hemisphere, before the 1800s, there wasn't anybody doing systematic observations, either with telescopes or any other way. So there's, first of all, a bias toward the northern hemisphere. And then there's also the bias to the period after about 1840 because of photographic plates and sky charts. I mean, remember, just as a side comment that may help, Neptune was actually recorded by Galileo. It was seen several times during the 18th century, but nobody realized the bugger was there until it was discovered in the 1840s because of the existence of star charts with sufficient astrometric and photometric accuracy. They were visual, but nonetheless, they were accurate, that allowed comparisons of fields. So when Gale et Daré managed to find the thing based on Leverrier's calculations, it was entirely because they knew where to look, but they also knew what the field would look like. Now, the problem with recurrence is that before that period, we just don't have an idea of what the sky looks like. And so people who were looking in that interval might have noticed or might not have. RS Oph happens to be very bright at maximum. It goes up to about 5th magnitude, which in that part of the sky is significant. Now, we also know, as a result of surveys that are being undertaken largely for gravitational microlensing, but also for just general transients, that there's a population in the Magellanic Clouds, in the LMC, and also in Andromeda. Because we're outside the system, we see the whole galaxy simultaneously. It makes it a lot easier to figure out if something's changed. These are objects, these are systems that recur on timescales as short as a year. We don't understand that process. But I want to make it clear that the physical instigation has to be basically the same. Okay? You're piling material on and getting an explosion. Now, the next point is, and if you'd like, we can go over some more details. I'd be glad to explain more in discussions. To explain something about what François was showing in terms of spectral evolution. Once the explosion occurs, you have two possibilities. Either the ejecta, the stuff that's been blown off, goes out into nothing or virtually nothing. That is, you've got the white dwarf in the binary, but the environment is pretty clean. In that case, you have something that's going to look here. So I've got to switch screens somehow. Okay, so this is what you would get in a normal nova. In fact, it's very close to the physical conditions of a nova. That is, you've got filaments, there's some hot gas inside, but basically everything is just thrown out ballistically. It's more, it doesn't matter whether it's spherically symmetric or not. I mean, basically, who cares about that? Okay, but it's not really changing the environment. It's just expanding, starts out optically thick, it cools, and you get filaments. On the other hand, as François was showing, the environment in which this explosion occurs is a mess. In fact, just to show you some models, this is actually what RS Oph probably looks like. Of course, not quite as colorful, but there's an accretion disk that forms around the white dwarf. This is the system seen sideways. There's material that's blown out of the system. It's accreting from the wind, and some of that is focused toward the equatorial plane, and basically the stuff is going to, in the environment of the white dwarf, give you a kind of thick disk. Okay, but you see that from the colors, and this is order of magnitude differences across the color chart, what the models are showing is that the environment is going to be filled with gas. And this gas, which is the red giant wind, has a density that's a lot higher than the interstellar medium, and in fact, a lot higher than an ordinary H2 region. It looks, in terms of density and composition, a lot like a molecular cloud. And this is very important for why one would want to study these systems. So I'm going to come back to that in a minute. The explosion, to show something that is as close as you'll see, looks like this. This is the Tesla test of 1955. It's a thermonuclear explosion, not a thermonuclear runaway. The only degenerates here were the politicians who were testing the weapon. But the thing I want you to notice is here, the first is the expanding fireball. This stuff actually is irrelevant. This is the cable that's being evaporated, and this is the tower that's supporting the explosion. But this shock, this surface, this optically thick structure that's expanding a hell of a lot slower than the speed of light, is here suddenly producing a vaporous phase around the fireball that hides the actual fireball. These are the narrow lines that you're seeing in the first flash spectrum. Okay, this is the flash ionization of the environment. Now, in this case, it's a condensation, but we know the process extremely well. It actually has some similarities to what happens in Plinian volcanic eruptions like Vesuvius, where you get the formation of a vapor cloud around the pyroclast when the explosion first occurs. This now expands, becomes thinner, and the shock itself here impacts the high density region, rebounds, and the subsequent evolution is the propagation of this reversed shock back into the ejecta. This doesn't occur in the same way in RS Ophuchi. But what you're seeing here, please pardon the jet noise. This is actually what it would sound like after the shock had passed, okay, but not before. So here, the buoyancy that you normally see in nuclear test films is because this is so hot, it's actually, and and low density. It's actually buoyant in the Earth's gravitational field. This doesn't happen in RS Oph or any of the symbiotic recurrents. Okay, so the part that we were looking at before is the only part that matters. Now, this is actually the way the explosion proceeds. That the expanding fireball here is filled with hot gas, and you can see the ejecta here blowing in this over on the right off the plane and on the left in the plane. Part of it is focused around the around the red giant. Part of it penetrates into that wind. And so you have this piston moving into high density, which is going to create a very high temperature region, and then a lower density that's escaping out of the density gradient of the wind. Okay? At this point, by 20 or 30 days, something very dramatic has happened in these systems that doesn't happen in an ordinary nova. I said, you're throwing this out into a miserably dense environment and a dirty environment. Depending on the kind of system, there may be some dust mixed in. Composition may be different than solar. Carbon rich, for example, which isn't unusual in evolved stars. That material is being swept up in the ejecta. Now, you've got to think of this not as a piston, but as a region of high pressure that's moving into the background and accelerating the background with it. Any of you who have ever stood on the platform in a train station or on the sidewalk when a train or a very rapidly moving truck goes by will know exactly what's going on. That after the passage, the material, the detritus on the ground, leaves, papers, and whatever, have been accelerated. Okay? They're moving not at the velocity of the piston, not at the velocity of the train, but they have had momentum imparted to them. So when we talk about the shock, we say that there's this surface and material is flowing through it, but in fact, what's happening is this is expanding into, accelerating, and engulfing this background material. Consequently, this is a very big difference from the classical nova. Both the mass of the ejecta and its composition are changing in time. I have to emphasize this because it completely changes the way you understand the spectra. If you were looking at an ordinary nova explosion, it would be the ejecta expanding outward like the fireworks with a central source that's just ionizing it. And so the outer part recombines, turns dark, and then reionizes. And the whole story is looking at the way that the ionization reveals different levels, essentially like a CAT scan. Now, here it's fundamentally different. Here we have an active driver. This shock going at a few thousand kilometers per second is virtually the same as a supernova remnant in the interstellar medium. The process heats the gas to well above 10 to the 7 Kelvin. The gas is only going to be able to cool through the continuum, so it stays bloody hot. And this produces a very strong, hard X-ray source. Okay? That source, on the other hand, is not going to have a substantial ionizing effect on the background because it has the wrong energy. But the gas that's cooling behind the front, that can start to form emission lines in the part of the spectrum you're used to seeing. That is, the helium lines, the recombination lines, the Balmer lines, which are already out here. And the other thing which is essential is that this shock has in front of it an ionized region, the so-called precursor. That's what you saw in the nuclear explosion. That's what causes the condensation. That stays active for months. And as the material gets swept up, and as the shock itself cools because of the expansion, because it's doing work on the background. So it's imparting energy to that. This is another way of cooling. The temperature drops dramatically in this first couple of weeks as this expands in a way much different than a classical ejecta. Okay? The central source is playing virtually no role here. And because of that, you get all of the recombination lines that you were seeing, and they're narrow. It's not that they're so narrow as the wind itself, because they're probing different portions of the wind, not just the outer part here, but also the inner part. Okay? Now, to show you that essentially all of these systems behave the same way, or that at any rate, you see the signatures of them. I'm showing here a comparison between two different wavelength regions in the very earliest stage of the Echelle spectra that the group has been taking, where the blue and the red are V407 Cygni, which went off in 2010. This is a spectrum from the knot at a resolution of about 70,000. The reason I'm showing it isn't because there's any similarity or overall similarity in the spectra. In fact, by this point, this was almost 25 days into the outburst, the outburst itself, the shock, was already thin. You weren't really seeing it. You were seeing the material that had been swept up. That's why you see these broader lines. The thing I want you to notice is the incredible coincidence between the narrow lines. Those are the precursor. That's the wind. That's the stuff that hasn't been hit yet. That's the reason this is so important. We're seeing the whole environment, the explosion, the region into which it's moving, because we knew the system before this happened. That was the other thing that I want to underline in what François said. One of the great advantages is, never mind that this bugger went off 5 years too early. Maybe it just had indigestion. The thing that's important is we know what the system looked like even months before the explosion. So now we know what the shock was going into. If we want to understand the physics of the shock, then transfer that to the understanding of supernovae, transfer that to the understanding of gamma ray bursts, transfer that to the understanding of breakout jets in active galactic nuclei. We can do that. Nature has provided us a very special, not laboratory, not experiment, but demonstration case. In 1985, we had ultraviolet observations along with optical, but that was the Stone Age. We barely had CCDs. In 2006, we didn't have the observations sufficient in resolution to interpret what was going on in the UV, but we had the 85 outburst because of IUE. And this time, we have all of you. We have optical, high resolution, gamma ray, X-ray, the VLA, ALMA is online. So we're going to have molecular observations and millimeter observations, probably for years. The European VLBI network. And on top of that, the Fermi Gamma Ray Observatory and the Hess Cherenkov telescope that have detected this source at MEV and GeV. In other words, this source, this shock, this thing that we're going to be analyzing, has accelerated the material of the red giant wind in exactly the same way as a supernova accelerates the interstellar medium to the energies of cosmic rays. The source has just been detected as a synchrotron source. That means the electrons have been accelerated to probably gigavolt energies, similar to those of the, well, actually higher than those of the protons. Consequently, at this point, we have nature giving us the information with which we're going to be able to disentangle 30 years of trying to understand something as simple as a supernova explosion and its interaction with the ISM. This is just to show you a couple of other parts of the spectrum, just to emphasize this. This is on August 25th, and this is a comparison again with the day 21 of V407. You see that here you've got the shock line, here you have the shock lines, but every one of these narrow lines, this is not noise. Every one of these has a correspondence in the red giant envelope. This is no longer the flash spectrum. This is late enough that this is now the spectrum being generated by the shock. Another example, in this case, the H gamma line, which by this point was much narrower in V407. This is the line that Francois was showing of iron, but all of these are iron lines on top of helium lines. Okay, last point. As the shock expands, and this is the pre-outburst. So this is what the H beta line looked like from the wind. Okay, it was a maximum velocity of less than 200 kilometers per second. So yeah, there was some mass loss from the system. But what you see in the course of the first days is the ionization of the wind by the shock and the loss of this line. The same thing here, showing the H beta line and the H gamma line. All of this is overlying material from the red giant wind. And this is where it's just been ionized away. The shock hasn't reached it yet. It's just gone. Actually, this is going to turn over into emission. It just hasn't yet. The oxygen 1 line, some of these Francois showed, so I'm just going to skip over them. The one thing that I will just mention is an intriguing possibility, and that's that the green line is one of the helium lines, and the red line is the profile you would have if some sodium were being excited in the red giant wind. So I think there is some sodium emission, but it's got nothing to do with the shock. Okay, this is just another probe of the wind. Okay, all of these are in that sense related. Okay, so I'll go really fast now. I hope we can talk. This is the evolution of the X-rays as of yesterday. The gray is the 2006 outburst. This is seen from Swift, and the work has been unbelievably done by one of the angels of our business, Kim Page, who's one of the project scientists on Swift. The X-rays are gradually becoming so-called softer. In other words, the shock is cooling. And that's why this thing called hardness ratio, the high to low energy ratio, is dropping. This is where the central source will expose itself. It's not that it's turning on, it's becoming visible. This is the point at which the shock has finally removed enough of the overlying hydrogen that we can actually see the central star. And so, okay, one last point. This should also emphasize what François was pointing out, this is the pre-outburst and post-outburst at H alpha of this source. This is a difference of months. There is some general outflow in the system, but here you've got the shock. Now, one last thing. When you're looking at the explosion of just ejecta, the maximum velocity you see is the maximum velocity of the ejecta. It's very important to keep this in mind. Here it's not. That you're seeing where the cooling is taking place, but the actual velocity may be more like 6,000 kilometers per second, not 4,000. Okay, it's the same thing you saw in that fireball. You see the fireball because at that moment, it's emitting in the visible and it's cooling. If that were happening in a lower density environment, you wouldn't see it. And eventually, in the explosion, you would see the fireball, but the shock would be way ahead of it. And it would in fact be transparent. So, unlike what happens in the ejecta, because they're finite, here we see the stratification of the emission because it's probing where it can radiate, which means we can probe its temperature. This is nowhere near as simple as the symbiotics. You can think of a symbiotic star as something with a very hot lamp in the center. Somebody hasn't properly adjusted the bulb, so it kind of flickers, and the environment is dense enough that once in a while it can actually react on times of days to weeks to years. But it's essentially simple. Here we've got that and all of the other symbiotic phenomena in the quiet stage. In other words, where you're seeing this. But then it blows up. And so what we see is the bomb going off, the expansion of the shock, the readjustment of the envelope, all of which is going to take years. We know this from the V407 Cygni observations. In other words, not only is this a gift that is going to keep on giving, but how this develops over time is going to give us a very, very clear dissection, almost an anatomical dissection of the structure of the giant and of the binary system. Okay? Now, one last to show something from Alessandra's thesis. The evolution of the oxygen and the helium lines, you notice basically follows the same pattern as you saw in the X-rays. That is, these are decreasing in strength initially. That's exactly because it's cooling. So we're not seeing the line very much anymore. Then there's a point where two things are going on. One is the visibility of the central source, but that actually has nothing to do with the rest of the ejecta. The ejecta are seeing things we're not. What's more important is the shock eventually reaches a low enough density that it just goes into free expansion, and we see something that looks really much like an ordinary nova. This is usually called breakout. Just to give it an analogy with what happens in the atmospheric tests from nuclear explosions. Okay, we're not even there yet. And unfortunately, this is going to happen once the source is in conjunction with the sun. But by the time it comes out, it's going to be down here. And the part that's going to be really interesting is to see what happens in this later stage, 100 days or 300 days from now, when the system starts reconstructing. Now, to put this in perspective, kind of final perspective, this is not RS Oph. This is Kepler 16, I'm sorry, this should be 1604. Great way to cheat. I chose this one deliberately because this is the 450th anniversary of Kepler's birth. And maybe it's appropriate that an analog of the supernova that now bears his name should happen in the same year. But if we were close enough to this system to actually see it, this is what we'd see. It would be distorted from this because this went off in the interstellar medium and not in a stratified red giant envelope, but it's pretty damn close. Okay. So I hope this is explained a little bit of what's going on. I think at this point, if you still have the patience and the interest, we're most certainly open for questions and comments and insults. So I'll turn it back over to François and Olivier.
Thank you, Steve, for this presentation. And if somebody have a question to Steve or François, so please ask. You are just to put your microphone on, so don't hesitate.
Steve, this is Woody. What's the density profile of this composting that's going on at the surface of the white dwarf? And is there a density differential at that surface?
Neat problem, to the point where this is actually one of the thesis topics here in Pisa. Okay, there are two things that are happening, and that's the other reason why the recurrents are so damned important. The stratification is because it's being compacted under gravity, so that's certainly there. That's going to happen in any compressible star, and degenerates are compressible. You know, they don't have constant density. The envelope that's accreting has a lower density. It's also hotter, which is something I didn't mention. It's falling onto a surface, but there are two possibilities. One is that it just accumulates, and the other is like what you do in a compost pile. You stir it periodically. Now, when the stuff is accreting, it's coming in from an envelope, it's coming in from a companion that has angular momentum. So this isn't just falling straight in. It has some circular motion, which is going to generate a shear flow, much like wind blowing over a forest. And what must happen is that this mixes in some of the material from the envelope of the white dwarf, even in the region where the density isn't changing much. Okay? Now, all of you know that in a car, you don't just have the spark igniting the gas. This would be kind of stupid. You first mix it in a carburetor and get the gas and the air mixed together before you hit the spark. Okay? It makes a difference if you have pre-mixing or no mixing at the time of ignition. We don't know what effect that has here. My bias is that the pre-mixing is much higher in the recurrence than in the normal systems. That the normal systems are less massive white dwarfs. We know this. Maybe slightly less. Their rotations may be different. Something is happening that's different in the boundary because they blow long before they accrete the same amount of material. I should add that although the ejecta here by today will be almost those of a classical nova. And so you would think that everything like slow accretion and blowing off will work. All of this crap that's been accumulated from passing through the red giant has probably increased the mass of the ejecta by a factor of 2 or 3 already. So its subsequent evolution is definitely different than what a simple expansion would be. That's important because knowing how the material has mixed before the explosion, that stratification you were asking about, the density profile and the velocity profile, that changes the nuclear reactions, which changes the burning products. These are not just small open questions. If we can understand this, we can port this knowledge into understanding what happens in the ignition of different nuclear stages in stars. It just happens more slowly. It happens deep in the star. Here, we're lucky enough that it happens at the surface, but the physics is basically the same. Okay? I hope that answers the question.
Thank you.
Now, outside the region that's accreting, this is very schematic. Just one moment of just one thing on screen sharing that here. This is noisy. Okay. This is Genovese Pizzeria, so it's a little bit noisier than the ignition of a nova, but it's exactly the same process. Okay, this is long before the explosion takes place. It's the first couple of 100 seconds, and to show you the comparison, this is what the models show, which is a burning layer about a few 100 kilometers thick. And the material, once the explosion, once the nuclear processing starts, gets dredged up from below. Now, if this layer is pre-mixed, the explosion occurs differently. It's the same thing here in looking at the fire in the pizzeria. This is pre-mixed, which is why it's so efficient. This may be a hell of a lot more efficient than we think if we can pre-mix it.
Hi, Steve. David here. I've got a question about the white dwarf. Do we know whether it has a magnetic field and whether that has any impact on the process of the explosion?
Well, the first is it definitely would have an effect on the explosion. I think in this system we can say there is no field. At least not a field that's dynamically important in the accretion process. What it would do, and we know of magnetic white dwarfs that are novae. DQ Hercules is a great example of this. The 1500 Cygni is a polar, and probably Hercules 2020 is as well. These systems that show periods that look like white dwarf rotation periods that are much shorter than the binary period. If it's a very, very weak field, then some of it is going to be blown off in the explosion. That's inevitable because the magnetic field is going to freeze in. But the extent to which it controls the accretion or would control the way the TNR would proceed, I don't know. If the field is strong enough, it's certainly going to change the ignition of the TNR, that is of the nuclear reactions. But how that happens, nobody would know. It's also that the field may be confined to a relatively thin outer shell, so it controls the accretion and it's transported through the disk, but it may not reach into the deep interior of the white dwarf. That depends on the history of the star. This is also one of the fundamental problems with understanding the symbiotics. The environment around the white dwarf is very unstable. Even if the wind overall is so large that everything kind of averages out, it kind of looks quiet. By the time you get down to the scale of the white dwarf, you're dealing with things the size of London, you know, that tens or hundreds of kilometers make a difference. And fluctuations can occur on times of minutes or hours. So interpreting the spectrum of that environment requires first very high cadence, not just the spectrum, but the energetics, and then long periods to see what the average looks like. If you have a magnetic field in there, it just complicates things. The accretion onto a magnetic field, like what happens, no, I'll give you the best example I can come up with. If you put a magnetic field in this, you have the Earth's magnetosphere. Okay, the red giant has a wind that's much slower than the solar wind. It's going to be maybe 100 kilometers per second. The solar wind is more like 7 times that. The densities in the white dwarf vicinity are a couple of orders of magnitude higher than the solar wind, but nonetheless, the Earth is about the size of a white dwarf, okay? And this is a weak magnetic field in a relatively weak wind. So you could think of it as this 24-hour white dwarf that's doing this with a wind blowing past it, okay? It might be an interesting study to say, let's replace these two, because the Earth doesn't gravitationally deflect the solar wind, but a white dwarf is going to. It's a one solar mass object. It's as massive as the bugger that's blowing the wind toward it. So there's going to be gravitational deflection. There's going to be a disk formed. The Earth doesn't form an accretion disk. It forms a current sheet in the rear. It forms a magnetotail. But if there were a magnetic field, it would look a lot like the Earth's case. Okay?
Yeah.
That will show up in symbiotics. I don't think we see any examples of that here.
Okay.
And in the other recurrence, we can say the same thing. The effect of the field is actually to render inefficient the accretion. So having a recurrent that's strongly magnetic is actually almost antithetical physically. Okay?
Yep. Thanks.
That's neat. I hadn't thought of that. Especially what happens when you have the alternate presentation of the pole, because sorry for going on like this. Stop me if I'm saying too much. But if you've got the pole open and the stuff coming in at the poles, if you do this in an accretion disk like a dwarf nova, then the disk is everywhere. Here, the accretion is coming from the wind. So sometimes it accretes directly, and sometimes it's going to accrete at the equator. That's a mess. I think if any of you want to do a PhD, I think this would make a great project. That would take, like 10 years, but so does good cheese. So I hope that answers it.
Yeah, thanks.
Any other questions?
A comment, Steve. This is Gary Walker. I haven't been digging spectra, but I've been photometrically observing this almost every night. And I was noticing on the AAVSO light curve this morning that I expected things to kind of be in an exponential decrease of the smooth light curve. And I noticed very evidently that its steps, day to day. I observe about once a night, and it seems like at least 3 or 4 times I've seen where it has stepped down and then it has decreased less and then it decreased a little more per day.
Yeah.
Is that real, or is that just noise?
Oh, no. This isn't noise. This is dramatic information. It's the same thing as what happened with the disappearance of the helium line. The reason these things have never been seen is because nobody's paid that much attention or that much care to these things. You look, imagine, have you ever flown cross country or cross ocean?
Yes.
Taken a transcontinental air.
Yes.
Okay. And all of you, I think, have had the experience of just apparently flying on the level, and every now and then you hit a bump. These aren't logs in the stratosphere. These are turbulence structures that haven't dissipated. The red giant wind is not homogeneous. Okay. We have this idea that when you're looking at the flow from stars, everything just kind of spreads out. Everybody knows stars are nice and spherical and they look like billiard balls, except they don't have numbers on them. Okay, this is garbage. The wind has intrinsic instabilities. We know from the solar wind that there are structures, not just coronal mass ejections, not just flares, but just ordinary prominences, differences in coronal holes. This wind is inhomogeneous on scales that are much smaller than the radius of a red giant. Okay, and this shock is expanding out into that. All you have to do is look at the films of nuclear blasts in the late 1950s, going up to the test ban treaty, to see that in the atmospheric tests, the structure of the fireball immediately starts to fragment. Okay, the shock isn't spherically symmetric. You have even in the cooling phase, I mean, you saw it in that film that you start forming patches. That's just in the expanding ejecta. Now, that's running into all of the structures that have been advected and are continuing to be advected out in the wind. Unlike the nova, where there is, unlike a classical nova, where you won't see this. If the central source is varying, then the nova light curve becomes complicated. But if you had a central source that was on and then off, and just expanding ejecta, you'd get an exponential light curve. Okay? Virtually no nova looks like that. And certainly none of these are going to look like that. That's why it's so important. The stuff you're seeing photometrically is the amalgam of the emission lines and the continuum. You're not seeing anything of the central source. You don't even know that exists. At this point, the emission from the ejecta and the shock are much, much brighter than the red giant, probably by 2 orders of magnitude. Eventually, you'll see the red giant, but that's going to be later. That's that phase that Schaefer has that's kind of flat. That turns out to be interesting, but for other reasons. But this decline that you saw in the plot I was showing of the helium and oxygen lines from Azzolini's thesis, that's the real dynamics of the shock. Again, remember, you're looking at something that's driven. It's not freely expanding. So the interpretation doesn't hold. On the other hand, in some ways, it's closer to your experience because you've never actually seen an explosion in space, except maybe in Star Wars. When the Death Star goes, it just goes, right? This isn't the this is the Death Star in the Earth's atmosphere. Okay.
Interesting.
Now, those fine structures are things we're going to have to understand deeply in the model that I showed you, we actually had those. I didn't explain how the calculation was done, but half of the computer time was setting up the environment naturally, just letting the red giant blow a wind out. And all of that structure, all of those filaments and colorfulness, that was what you're seeing now, running this shock running into. Okay, the world is only symmetric and uniform when we're teaching students. After that, we have to grow up and leave the nursery. And the kinds of observations you're all doing are the first chance we've had to see this. You know, nobody, let me reemphasize this. You have CCDs. You have photometers, but you also have CCDs. Those are 100 times more sensitive than photographic plate score. As somebody who grew up in the era of stone tools, I'll tell you that to be able to take one plate per night at this stage of the outburst was pushing it. If you had a 2 meter, you were lucky. Okay? What took in the 1960s, if you look back at the literature to the 67 outburst, the spectra that are shown there that took hours, you're getting in minutes. And you're getting them with telescopes that are 1/2 meter, and those were with telescopes of 2 meters. You see the difference?
Yeah.
You've entered into a world thinking that this is normal. And I'm telling you that this is going to leave a legacy for the future of a sort that we have never had. That's why this emphasis on keeping you up to date on what the physics is, so you'll realize you can ask these questions in ways we were never able to. I'm sorry to say it's a pity that we will not be able to get HST observations because the symbiotic community doesn't think this is important. But nonetheless, we are observing this with SWIFT, and we will have GRISM spectra. So we'll at least be able to go to about 6 electron volts. But the interpretation is going to be the combination of multi-filter photometry at high cadence and of all of the level of the spectroscopy that François was talking about. I hope that helps.
So let me ask another question. An all-night photometric run might be kind of worthwhile. I mean, at a cadence of 2 minutes per exposure, something like that.
At this stage, I doubt that very high cadence is going to be important because we're not seeing the central source. But it's going to be absolutely vital once the super soft appears, because at that point we will actually have a contribution from the white dwarf. And it may be that in B and U, you'll start seeing some very rapid variations. The shock itself is large enough that probably the shortest variations you'd see would be minutes to hours.
Okay.
But the very high cadence stuff is going to be essential for understanding the reinitiation of accretion. And that's true for all of these systems, for novae, always. And this is where the things generally fall down, because those who have access to large telescopes can't get the time anymore. So they're not going to be able to follow things with second time scale 2 years later. Every stage has its own physics. Every stage reveals something else, and none of the physics is particular, just the manifestation. So yes, but not yet.
Okay.
You use the high cadence.
Sorry, Steve, We don't hear you.
I have no idea.
Okay.
Where
That's
did you
fine.
stop hearing me?
Okay, no, that's good. No.
Oh, okay. No, for some, I don't know why. It just cut off. Maybe it was, this is artificial intelligence saying shut up.
Steve, this is Wayne Green. Don't shut up just yet. I study the ISM, so pardon my crappy question. What you've got is an explosion that's sending a light pulse out. And sure, the early days, it's hidden and so forth, but as the opacity opens up, we're beginning to get a probe that's roughly 200 AU wide per day. So let's look at those narrow lines that we're seeing in these features, the ones that are related to the ISM. Has anybody done a study on looking at just how lumpy the ISM is in that area as a function of, say, the irregular decretion rate from the giant solar or giant wind?
Let me see. First, let me emphasize that those narrow lines are not those are environmental around the white dwarf.
Okay.
They're not from the ISM. You're not getting out to densities of 10 or lower.
Oh no, I was referring to the wind.
It is circumstellar material. That's true. Yeah. But keep in mind that here you got a wind. So the circumstellar material is the wind. I mean, nothing stops it. So whether it's 100 AU or 100 parsecs, this has been continually blowing. And it's also not spherically symmetric. Some of it is actually flowing past the white dwarf and being focused in a wake. We know that because we can see the variations in time in the pre-explosion. Some of it is going to be, as you said, this light pulse that goes out. Now, we can look at it this way. If you had a pulse, any pulse that goes out into the medium and it ionizes it, then the decay is going to be the recombination time. If that recombination occurs in days, it implies a density of about 10 to the 7 or so. 10 to the 5, 10 to the 7, which is a couple of orders of magnitude higher than an H2 region. But it's not that much unlike a planetary nebula. On the other hand, the oxygen 1 line is telling you it by its presence that, and then its absence, that whatever this pulse is, it's not a single pulse, it's followed by continual UV emission. That was what I meant by the precursor. Now that's going into a dynamical environment. If there were in the background medium, actually in the interstellar medium, enough dust, you might see a light echo. I doubt that here because the explosions occur so frequently. But there might very well be some record out there of material that had condensed out of the wind that wasn't swept up.
Well, if I did my math right, it's about 200 AU per day would be the velocity of this. Let's don't call it a pulse so much as the flashlight. So the flashlight, as it's going out at that rate, will be encountering new material. Older material will be in its various states of recombination, superimposed together with newer and newer and newer material as we go. So that we're talking line of sight. So we're also, I don't know what the inclination of that system is with respect to the line of sight.
Not eclipsing, but that really doesn't matter.
We're right on that, and you would we would see that it's kind of a Bondi-Hoyle accretion effect or even a magnetic lensing effect in there. But the result of it all, what I was kind of getting at, is it seems to me there's some information in those thinner lines that are not necessarily, they're close to, they're proximal to the system, but they're not part of the system itself. In other words, not within,
absolutely. We saw that in V407 Cygni.
So how important it is for this community to be monitoring and paying attention to those narrow lines?
If you can see them, you've got a problem here. It's signal to noise.
Yeah.
But absolutely, that's why I was showing you the example from from Cygnus that this happens to be the longest time base we have. We followed it for a couple of years so we could see this differential recombination. There's another point that you got to keep in mind. This is a system which created two pulses. Okay, the first is the initial expansion of the shock, which is the highest velocity. The second is the continuing precursor. And all of these are going to be superposed. So when you say narrow lines, you, I think, need to distinguish, because the terminal wind that becomes the circumstellar interstellar medium is still going to have velocities of tens of or even higher kilometers per second. And you're going to see the emission from everywhere. With different time scales. There'll be delay times also, depending on where and the geometry and where the recombination occurs. So absolutely, I would urge people to follow these spectral developments for as long as you can, but with a caveat. It's a very nasty one. These lines are going to have widths of less than 100 kilometers per second. Okay, that means you're going to need resolutions of 5,000 or higher,
Yes,
to follow these lines. That's going to require a bit of aperture, not just exposure time. And they're going to be weak. I can tell you which lines would be the best to follow, and those are the principal forbidden lines, like argon 3, which is in a very good wavelength region for all of you. The hydrogen lines are, well, I have a bias. The hydrogen lines are nice, but they're hydrogen, so they're everywhere. They don't really tell you very much. The fine structure will, and monitoring the structure of the Balmer lines will be important, because you can do that at lower resolution, because they're going to be much brighter. But they're going to be coming from everywhere, and the recombination times are going to affect the line profile tremendously. But yes, do it. And I would never say don't do it, never.
well, you've definitely made a case that I've been preaching here lately, and that is, we need bigger telescopes, so we need spectrograph to go along with the focal lengths of those big telescopes, so that we can get after this kind of stuff. And I really appreciate the work the community's been doing with the shell spectra, because I think that's where a lot of these data are going to be. Until we get into those resolutions, then there we are. But thank you, sir. Thank you.
Look, let me tell this community, LSST, otherwise known as the Vera Rubin telescope, is going to come online within the next couple of years. This is the Large Synoptic Survey Telescope. The principal thing this telescope is going to do is give a gazillion object transients per night. Okay, you're going to have follow-up, literally in the Americans phrase, out the wazoo. You're not going to know where to turn, because this is going to produce supernovae, novae, GRBs, intermediate level transients all over the place. Okay, the thing I'll urge is persistence. The thing that distinguishes what you can do from what the rest of the community is going to wind up doing is that they're going to stop at saying, well, we've identified it. Good, we know this is a type 2A supernova and not a 2P. Okay, because the first few spectra show this, and that's where it's going to stop. The problem we've had in understanding the physics in astrophysics is that these things take place on timescales that frequently are shorter than the age of the universe, but longer than human lifetimes. They have to be followed. Just identification is not enough. Okay? There are ways of recovering some information even from lower resolution data, if it's very high quality. There are tricks you can, there are tricks that allow you to do certain, to certain limits, to super resolve things, for example. But you have to know why you're doing it. So I'll urge that. As far as larger telescopes, 1 meter is enough. The sorts of things that need to be done, 1 meter with a good spectrograph is enough. The difficulty with the Echelle, as I've had to fight over the years with people who say that you can't calibrate absolutely Echelle spectrographs with fibers, is that the vast majority of Echelles are fibers, which is fine, provided you have slit spectroscopy and slit photometry and absolute spectrophotometry at the same time, or you have really good control of what you're seeing is. Okay, there are ways of getting more information out, but simply having more Echelles is not the only answer here. It depends, again, are you looking at profiles? Are you looking at distributions? Are you looking at energetics? All of these form part of the same questions. If you put the physics first, you'll see what the answers have to be.
Any other question for Steve or François?
Steve, Hamish Barker from New Zealand. What's the effect or the magnitude of the speed?
I'm sorry,
of
I
the white
can't.
dwarf?
I can't hear.
Hamish Barker from New Zealand. Just wondering, can you hear me now?
It's still pretty poor. I'm sorry. I'm partly deaf.
It's in the chat.
Oh, that's okay. Okay, so if the white dwarf is a rapid rotator, would you have a difference between the polar and equatorial? Is that the question? Okay, yeah. And that's about all I can say as a direct answer. In fact, we're working on this. That's why I'm so excited about the question. There's a very peculiar thing that every child knows, that if something is rotating, you have in the rotating frame a centrifugal acceleration. Okay, now if you think about this, if you're accreting onto the equator, then this material has to co-rotate eventually with the surface, which is this boundary layer. But if it's on a rapidly rotating star, then there's additional support against gravity in the co-rotating frame, okay? So the pressure gradient is lower. This should change where the ignition occurs. Now, I have my own bias here, so I should explain this is something I'm working on with Jordi Jose. What we're trying to do is ask, since you will have reduced pressure at the equator, does the triggering occur at the poles first and spread down to the equator? Because the poles have higher gravity. The equator has lower gravity. So the trigger occurring at the same pressure occurs deeper at the pole than the equator, which sounds just the opposite of what one might think. Since the equator is heated by the accretion, you get a circulation. Material can be transported to the poles the same way that heat is transported in the Earth's atmosphere toward the pole from the equator. That is, you get a circulation pattern. So the idea here is the material accretes at the equator, is transported toward the pole, triggers at the pole, and you get something more bipolar than spherical. Now, we don't know if this is going to work, but the expectation is that the white dwarfs must, in these systems, in these symbiotics, the white dwarfs are not co-rotating. Okay, in the normal nova, you've got two stars that are really close together. I mean, within a solar radius of each other. So they can tidally lock, and the white dwarf can be rotating with nearly the same period as the orbit. But in these wide systems, there's nothing to tidally lock it. It's just being spun up continually by the accretion. Okay, so I think your question is not just pretty, but central to another one of these differences between these systems. I wish I knew the answer to this, but we've been working on it now for about almost 2 years. The pandemic has slowed things down because we can't be together. But a part of this is also being done as a master's thesis. I don't mean to sound as if I'm doing publicity. It's just, they're neat kids. Marco Bellomo, one of my students, is looking at the accretion problem and the formation of boundary layers. And the same thing is being done in Kiel by Wolfgang Duschel, and in Tübingen by Willie Clay. It's more than a technical problem. It's kind of at the boundary of what we understand about accretion disks. It's just we've managed to sweep it under the rug for the last 20 years.
Maybe one last question for François or Steve. No question? Okay, so I think we close this meeting, and I would like to thank you again, thank you very much, Steve and François, for their presentation. It will very great moment. So thank you again for both of you.
Thank you all. And
okay, and so I say you goodbye, and we will put this video on the Sheliak YouTube channel. I think tomorrow morning.
Recording
So no problem. You can see it again in replay tomorrow. So goodbye to everybody.
for anybody who could actually stand watching this more than once. But
Thank you.
Bye,
Thank you. Thank you very much. Bye-bye.
Grazie a
See you soon.
tutti. Grazie.
Thank you. Thank you.
Thank you.
very
Bye.
much.
Thank you.